So I'm teaching this like you have no experience in this, okay? So we know nothing, okay? So when we know nothing, mathematically it's more critical, okay? So let's form the limits, okay? So the first thing we're going to do, okay? So I'm going to analyze, okay? I'm going to analyze. So I'm going to, well, not analyze, we're going to assume positive shear and positive bending moment. So what that actually means is this, okay? So always remember the geometric datum is always on the left hand side. So this is our geometric datum. And geometric datum will not change at all. Okay, so this is your geometric datum. Okay, later on, I will tell you why the geometric datum is always on the what? Left hand side. Okay, so there are two ways that you can analyze this. You can analyze from left to right. Okay, or another way to analyze this, sometimes is important to analyze. Okay, analyze from right to left, two different directions. Stop me anytime if you think I'm going too fast. So left to right analysis means it's going this way. Okay, so this is left to right. And right to left analysis is going the other way. So this is right to left. Okay. Regardless whether you do left to right, right to left, geometric datum will never change. Okay, geometric datum will always stay there. Okay. So when we do left to right analysis, right? So this is our geometric datum. This is our slider X, right? Variable. Okay, so variable X means at every position we know the shear force and bending moment trend. Okay, so when left to right, the shear force is assumed to be this way, and the bending moment is in that direction. Why is because this is because of the assumption we make there is positive shear and positive bending moment. Okay, and then if we were to assume from right to left, or we are going to do from right to left analysis, geometric datum still stay. Okay, the distance from here to here is x. Okay, and then this length over here is your L minus x. Okay, L is the entire length of your structure. Okay, so you draw your beam. Now remember, this is still positive shear and positive bending moment. Now the shear force goes up, and the bending moment is in the clockwise direction. Okay, so you can see this is from left to right analysis. Over here is from right to what? Left analysis. Okay, so you have to get this clear first. Okay, so for this case, I'm going to focus on left to right. That is why I'm not bothered about the reaction. We don't need to find the reaction at point C because we are going to do what? Left to what? To right. Okay, so now we are going to now do between point A to point B. Okay, so we're going to draw form the shear force and bending moment equation. Okay, so we're going to do from 0 x to A. Right, so this is point A to point B. All right, so point A to point B has a evenly distributed load. Okay, so with an evenly distributed load, so this is my point A, right? This is our geometric datum on the left hand side, so this is x, right? So over here, the evenly distributed load, we have omega multiplied by a distance of x. Sorry, omega x. right? The longer the slider x, the higher is the equivalent load. So that's why we call it omega x. And the distance from here to here, this is x over 2. Okay, why x over 2? For evenly distributed load, the equivalent load is at the exactly at the center of the beam or of the variable. That's why it's x over 2. Okay, just to quickly recap. So now we know that we are going to assume positive shear, positive bending moment, v as a function of x. Okay, moment as a function of x. Okay, and then the next thing that we do is we're going to carry out static analysis. Okay, so when we do static analysis, first we do summation about forces in the y direction is equal to 0. So you have minus omega x minus v as a function of x. The whole thing will be equal to 0. So v as a function of x is equal to minus omega x. This is your equation number 1. Omega is small letter, not big. I do apologize. Okay. And then we take the moment next. So I mentioned about moment at point z, or about point z at a certain distance x. So where we are taking a moment is we are taking a moment where I'm drawing the dot now, where you see the dot. Okay. So over here, you form your moment equation. So the omega x is going to do anti-clockwise, so it's positive. So omega x multiplied by x divided by 2. All right. And then plus by m as a function of x is equal to 0. So m as a function of x is equal to minus omega x squared over 2. Okay, so this is your equation number 2. So now this is from A to B. Okay, so next thing that we're going to do is we have to find the distribution from B to C. Okay, so we're going to do this. Okay, so to find B to C, so you're going to say or. Okay, let's find what is going on at point B. Okay, let's go. So at point B, okay, at point B, where x is equal to a, right? At point B, x is equal to what? A. So what do we have over there is if we substitute, so to find the shear force, magnitude, we're looking for the magnitude because now x is equal to a. Okay, so it's going to be a constant. It's not going to be a variable. It's not going to be a function of x. Okay, so the shear force, okay, shear force magnitude using equation 1, right? So you have V at point B is equal to what? Minus omega A. Okay, so this is a constant, as I said. So you know that there's a constant, and then you have bending moment magnitude using equation 2. Okay, so moment at point B is equal to minus omega A squared over 2. Okay, so that is what is happening at point B. So will ask me, Eugene, why are we looking at point A to point B to point, then B to C? Okay, how you section this is dependent on how the load is distributed or how the load are loaded. So from A to B, you have a what? Evenly distributed load. From B to C, you have nothing. Okay, so that's how you section them. Okay, so the next one is between point B to point C. So A, X to L, right? So we're going to sketch from here to here. Right. So this is between point B to point C. Okay, point B to point C. So to look at point B to point C, so we have so this is our point A, right? Point B to point C, where we're not looking at point C. So our variable now from here to here is X. Okay. Now between A to B, the even distributed load is not going to change anymore. It's going to be a constant because this is between point B to point C. So this is equal to what? Omega A, right? Because this distance over here is omega. I mean, this is even multiplied by A. And then we know the confusing part that some students make mistake is this, okay? The distance from here to here is A over 2. And then the distance from here to here is X minus A over 2. Okay. Why this distance is important? Because later on, we're going to take moment about here. That's why we have to know that distance, okay? Then again, we assume vertical shear and bending moment, positive shear and positive bending moment. So we're going to do static analysis again. Okay. So summation of forces in the y direction is equal to 0. So you will have omega A, right? And then, sorry, minus omega A minus by V as a function of X. So V as a function of X is equal to minus omega A. Okay, then you take moment again. So I mentioned about moment, Z about the variable X location, the whole thing is equal to 0. So now you have omega A. So it's going anti-clockwise. Omega A X minus A over 2, right? And then we have plus M as a function of X. Okay, the whole thing is equal to 0. So M as a function of X is equal to minus omega A X minus A over 2. Okay. Then you open up the terms, you open up, get rid of the brackets, omega A X minus plus by omega A squared over 2. Right. So there you go. Okay. So now once you have this now, okay, let me see, did I form anything wrong? Omega AX minus plus. Okay, it's correct. Okay, so you have equation number 3, equation number 4. So now we are going to sketch our shear force and bending moment diagram. So I'm going to copy this diagram. Okay, I want you to see how this is related. So I'm going to change this to. So far, any question? Are you okay?
Yes.
You're okay,
No
right?
questions.
Okay. So we're going to. Okay, so we are going to do our shear force diagram. So if we look at our shear force equation, we are going to stop at minus omega A. Okay, so everything will be in the minus form. Okay, negative shear. So this is our X. Okay, and this is our shear force. Okay. So now, let me go. So remember, over here you have your X distance, and over here this is your shear force. Okay. Remember, I told you guys that the geometric datum is always on the left-hand side. And the reason why, because when we draw the shear force and bending moment diagram, 0 is always here. So you cannot shift you cannot like happy, you know, shift here, shift there. You can't do that, okay? So over here is your distance A. Over here is your distance L. Okay, I'm just eyeballing this. So now, so you look at from 0, right? From 0 X to A, you have minus omega X, okay? And it will stop at minus omega A. So at a certain point down here, right? This is your minus omega A, right? So if you look at the function, it's linear.